Hi, everybody. My name is Nick Mackovski. Today, we're actually going to be going through the NIBP Nano system. So I'm the scientific support specialist with 80 Instruments, and we're just going to be basically covering the key aspects of the NIBP unit, what comes with the unit. We're also going to go through some theory of operation and some common some common pitfalls that we could, that we can avoid when using this system as well. Then, of course, I'm going to do a live demo with the unit, and we're going to collect some data, basically to show you the whole range of what this unit can actually do. So, what does the NIBP? What's it primarily used for? Well, obviously, this is used as it is a continuous recording system for non-invasive blood pressure recordings there. So this is done via a finger cuff system. If you're not used to, or you're not actually seen the NIBP systems before, these are primarily designed by Fingerpress Medical Systems, so otherwise known as FMS. So these companies are an industry leader when it comes to non-invasive blood pressure measurements. And at ADI, we do partner with such esteemed companies such as FMS, and we are able to basically connect our software and integrate it with their hardware, so that way we can record some of all of the parameters within LabChart, so fairly easily. So you can see the system down here is just the basic unit we have, and we have the interface here, and also the height correction unit. So all these aspects I'll be going through today. And here on the right is just a basic finger pressure pulse wave that you'll actually see throughout the webinar. So what are the key advantages of this system we have? Obviously, this is non-invasive. As it is non-invasive, it is actually very easy to use. Because it's a simple finger cuff, it's very easy to teach people how this works. So I have personally seen this system not only used in research, but also used for education purposes as well, as it's very intuitive, and you do collect quite a lot of data from just one simple cuff reading. With this compact design, it's able to be less invasive around the wrist, and also with the compact design, there's only one cable that actually connects directly to the NIBP interface module itself. This sort of system can be used for a range of different applications. It can be used anywhere from 5 minutes to half an hour to even up to 24 hours or longer. They're particularly used in cardiovascular stress testing. So if one was interested to see how someone's heart rate variability changes over time, under different sorts of psychophysiologic conditions, or maybe they're seeing how they're working post recovery of some sort of cardiovascular disorders, then this can be a good tool to use for that sort of experimental analysis. This system also, as we know, does integrate with LabChart. So other extensions that we have provided in LabChart provide also an estimation module for measuring cardiac output and stroke volume based off the non-invasive blood pressure unit here by FMS. So we'll cover that also in the webinar. Due to these long-term measurements that some subjects or some practitioners use, this system also has a 2-finger cuff switching mode. What this simply means is that over time, that if one finger becomes discomforted due to the constant pressure increasing and decreasing within the actual air bladder of the cuff, then a subject may find over time this may be uncomfortable. That's why we have 2 cuffs. That way you can switch from one cuff to another. And I'll talk about this a little also in the webinar. And of course, when we have collected our data, LabChart has fantastic types of modules for hemodynamic analysis, whether they are blood pressure modules, if you're looking into specifics of the waveform, or if you're more interested into the heart rate variability of your beat-to-beat data. So we'll break this down to the different, parts of the unit itself. So the first thing we're going to talk about is the wrist unit, this unit right here. So if you're familiar with FMS at all, we have sold these units in the past, and we've had the predecessor to this was much bulkier. So now it's a much more compact design, very simple to use here. So the case assembly here, the actual one cable that just connects directly to the NIBP unit next to me here. So it's just one cable. So this simplified version, there's less fuss at all when working with it. The instrument itself has, basically you can connect two cuffs. So you can have C1, C2 here. So you can see this person has one cuff on their middle finger and one on the index finger there as well. You don't have to have two cuffs. You can just have one cuff. That's totally fine. And the demonstration I'll do today will actually go through just using one cuff. The middle port here is just a port for a height correction unit, and we'll go through that very shortly. So that's all connected there as well. It's a very compact and easy to use design. And we also have a strap that goes around the wrist. So that way, if a subject needs to move their arms, above the head or in whatever fashion, then that will be securely fit in place. So the height correction unit is a really important aspect of this tool. Primarily, look, we're interested in mean arterial pressure here. So as we know that if we move our hands above our head, then the pressure within our hands is going to fall naturally. So that does not necessarily mean that is going to be an accurate representation of our mean arterial pressure at that time. So what this does, the height correction unit, it essentially compensates for that type of movement. This is done by using a line here where one side is the HCU transducer, as you can see, and this would actually connect to the cuff. So if I go back here, you can see here, that's the HCU transducer that'll connect to the cuff. The other side is a reference end. So this reference end is actually going to be at the same level as my heart level. And within this line itself, this is actually a clear tube. Within this clear tubing is mineral oil. So within the actual reference end, there's actually a bladder there of all the mineral oil as well. And so basically, as we move our arms, the HCU has a low pass filter, it applies like a low pass filter. And that's added to the finger pressure. And therefore, any slow changes we see is actually compensated. And so that's something I'm going to demonstrate to you later on in the webinar when I actually do some of these movements. So you'll actually see in one channel where we just have the finger pressure, the raw finger pressure, where that pressure will drop when I move my arm above my head, whereas the HCU pressure will be the compensated pressure. Therefore, that pressure will actually be similar to what it was when my hand was actually around the table here. And basically, obviously, we have our lemur connection, and that moves to the center of the NIBP unit. So we just have two ports here, one lemur connection for the cuff, and also we have one for the air hose, and then for the HCU as well. So a bit more about the application on how the HCU works is that the first thing to do is actually we want to zero the HCU unit. So what I'm going to show you is that we connect the transducer and the reference end together, and in the software, we're actually going to click in the settings, the NIBP settings rather, to zero this. So that way they're at the same level. Once that's done, we can just simply connect the transducer to the finger cuff and then have the reference end somewhere around the heart level. So that way the pressure will stay at a stable reading. So you can see the subject here has a reference end here. Yeah, that's fairly simple to use. So obviously that's going to compensate whether you move up or even further down as well. The finger cuffs are probably the most important part of this actual NIBP unit itself. They comprise basically of three different sizes here. So you have blue for large, medium's beige, and small is white. They're comprised of obviously a lemur connection that goes to the NIBP wrist unit and also an air hose. So this air hose then will connect to the air bladder that's inside of the cuff. So you can actually see here the air bladder would be in these cuffs here. And we also have the Velcro strap around. So technically, you'll be putting this on one of your fingers, really, probably the middle or the index, and we put it in the middle portion of the phalanx right there. So either here or there, we want to put it. So that's what I'll show you as well later. What's really important, though, is that there is an LED here, and there's also a photodiode. So the LED is going to emit an infrared light, and this infrared light will pass under or through the finger, rather, and then be captured by the photodiode. And as we're using infrared light, depending on how much blood there is within the arteries, will depend also how much of the infrared light will be absorbed. So technically, during systole, as there's more blood within the artery, more of the light will be absorbed, and vice versa during diastole. So with the cuff handling, with the actual kit itself, you're given first a cuff size guide. So we'll show you how this works after we finish with the slides. But basically, you're going to wrap around a little strap around your finger, and you're just going to move it back, and you're going to have 3 different points here: white for small, beige for medium, and blue for large. And depending on where the end of the strap goes, that will give you an estimation of what finger cuff you're going to need. Keep in mind, if you're kind of in between between large and medium, which mine is, then we would always recommend going for the smaller cuff, as a better fit will improve accuracy as well. Putting on a cuff just simply means that you just have to unstrap it. But this is a bit of a misleading image here, which in the fact that you'd actually unravel the top portion here, but the part where the LED, the photodiode, and the air bladder is, that's fairly fixed. We don't actually want to unravel that, because that could actually jeopardize the unit itself and damage the cuff. If you do damage a cuff within LabChart, when you're actually starting to run with the data, you'll notice that the data will tell you that there's actually a leak with the air cuff. So when that happens, you'll just have to replace it. So here's a cross section of the finger. So you can actually see here, obviously we have the bone, we have the arteries, and we have the LED and the photodiode there as well. What's really important is to keep it in this position. You don't really want the LED to be placed, higher up on the finger, and then that way it has to pass through the bone. So what this is going to do is just not only give you incorrect readings, but the readings will also be very noisy as well. So we kind of want to keep it in the same position as best we can, or the best placement as we can. So the NIBP wrist unit with the cuff and the HCU all connects with one cable that all connects to the NIBP Human Nano interface. So this simple unit here, just all it has is one connection, and you have a very important symbol here. That's the body floating symbol. That just means that the subject is isolated from any electrocution, of course. So this is totally safe to use for humans. Shouldn't be any problems there. So the back of the NIBP interface, you can see we have a switch to turn on and off, and we also have our mains power as well. So, we also have one USB connection here as well. So how this works is that we would simply connect this directly to the computer. So one big thing that, if you're familiar with 80 Instruments software and equipment, is LabChart tends to go hand in hand with PowerLab. With this particular device, we are giving you the freedom that you don't actually need to connect your PowerLab to it. You could directly connect to the computer. This is because we're using something called an NIBP device enabler. With some third-party companies that we partner with, we have integrated specific enablers that you can actually turn on within the feature manager of LabChart. And therefore, when you actually turn on the device, such as the NIBP unit, and open up LabChart, what you'll notice is the screen that will show you that the NIBP unit has been detected. Once that's done, you can just simply open it up and just go on, I'll go through some settings and click on New, and then you can immediately start collecting the data. So you don't actually have to connect to PowerLab. this is currently only working with LabChart 8 for Windows. That being said, I actually do have a PowerLab connected here as well. And if you wanted to, you could technically, run a PowerLab at the same time. So I'm going to run some ECG data while using the NIBP. So that way it gives you the freedom to keep collecting data from other, instruments at the same time. The NIBP device enabler also has a settings file that enables you to use the older version of the NIBP unit. So that's the ML282, if anyone ever uses that. So what parameters are we actually measuring here? So you can actually see some of the signals we can see here. And on the left here is just actually these are all the parameters we'll be looking at. So obviously the first channel will be finger pressure. That's clearly, you can see that. The HCU pressure. So that's the height correction unit pressure. So that's the pressure we really should be looking at if a subject tends to be moving their hands around a lot. If they happen to be, stationary like I am and not really moving around, then, the finger pressure would be, totally fine to use, provided that the actual unit itself, your hand, what I should say, is fairly in the same level as the heart level, so it should be a good representation. Obviously, we have a systolic, diastolic readings here. We have mean arterial pressure. We'll have heart rate channel as well. And you can see here, these are all separate channels. And this is just live data. So you can see that we have the parameters here. Well, the scales, you can see them there. So we can increase and decrease these scales. We have our time on the bottom here. And you can actually see what these are. So telling you, mean arterial pressure, diastolic, heart rate, and actually giving you the correct units as well. So this is all actually done automatically. So unlike other things in PowerLab where you normally have to calibrate, with this, you just have to plug and pretty much play. That you don't have to really worry too much about it. So the actual software within the NIBP unit, that'll do the calibration itself. We have some other quality control parameters that I will mention to you. So things like Autocal quality tells you the actual how good the signal is actually coming from the LED to the photodiode. We have an Autocal countdown. So we'll talk about that a little later on, but that's basically talking about how long it takes between one auto calibration to the next. And the reason why there is auto calibration is this system does require over time to correct itself because the theory behind this is to unload the artery. If you've never heard of that term before, that's okay. Basically, what we're doing here is that, as we know, systole, the artery expands, and diastole, it constricts. The point of this is we want to have the diameter of the artery the same all the time. And the way we can do that is by equaling the pressure in the cuff to the pressure within the actual artery itself. So that way, when the cuff pressure equals the pressure within the artery, then the diameter stays the same. Therefore, the diameter will be unloaded. And as the pressure stays the same, as the pressure changes constantly within the cuff, this way it gives us a representation of what the actual mean arterial pressure is within the fingers. And we also have other options here for like, NICO options. So this is to do with the cardiac output. So we can actually have separate channels for measuring cardiac output or stroke volume as well. So expanding a bit more on the NICO, this is just an extension in LabChart as well. So basically, when we're collecting our finger pressure data like this, we can have extra channels here where we can actually measure or estimate cardiac output into two various methods. So the Windkessel model 3-element is one method, and the Liz-Gestran method is the second. So these are very well published estimations of cardiac output. I'm happy to share with you some publications of these later on if you like, but these once again are just simply estimations. Once we have collected our data, LabChart is excellent when it comes to analysis. So, hand in hand, when you do collect the blood pressure data, we do have modules that are specifically designed for use, when you're using the NIBP. So one of these is going to be your heart rate variability. So when you're looking at beat-to-beat analysis, this way we can check, the intervals between beats. We can look at normal versus ectopic. We can look at the actual shape of the wave as well. We can look at even the spectrum analysis as well. So quite a lot of people that are interested in heart rate variability are also interested in the power spectral density of the heart rate variability. So that's something we can provide with the HRV module. We can also do specifics with blood pressure as well. So I'll also talk about the blood pressure module. This basically will look into more to do with the waveforms, so to do with, max and min dp dt. We're just looking also at, maximum pressure, mean pressure, that sort of thing. So let's talk about more about the theory. So I think this is actually quite good to actually have a better understanding of, as when we try to, especially when things, go wrong, this has at least we can have some sort of understanding from the theoretical point of view of what could be going wrong. And that way we can actually resolve the problem fairly quickly. So as I was mentioning to you, this system itself uses the LED to emit infrared light and to be captured within the photodiode. So this system, because of this design, it's using a photoplethysmography. This technique is widely used to detect blood volume changes in vascular bloods. So you can see here what we mentioned before with the LED and the photodiode. So here's just obviously a picture of us applying it on the finger. The plethysmograph waveform. So normally, like what you saw earlier on, you can actually see this is the finger pressure. That's the end result. But the most common plethysmograph waveform is, we see is peripheral pulse, which is what this system is entirely designed on. As the infrared light is emitted from the LED and passed through the bed of blood vessels, it's also being absorbed naturally during systole and diastole. So if you can notice down here, we have arbitrary units of the plethysmogram. So this is just showing you how much of the light is being absorbed, being detected by the photodiode. So you can see that during systole, as there's more blood in the blood vessel, as is in the arteries, naturally less light will be actually being detected by the photodiode. Hence, that's why it's lower. But during diastole, the opposite's occurring as the artery is constricting. Because of this design, a physiologist by the name of Jan Panaz came up with something called a method called the volume clamp method. The method, as I mentioned a bit earlier on, loosely, was that it revolves around keeping the diameter of the artery clamped or unloaded in spite of changes in arterial pressure during each heartbeat. Changes in arterial diameter detected by means of infrared photoplethysmograph built into the finger cuff are opposed by a fast pressure servo controller that changes the pressure in the inflatable air bladder, which is observed, which is also mounted on the finger cuff. So you can see here with the volume clamp method that, obviously this is a very crude image here, but, during systole, arteries expand. But here's an image with the cuff around the finger. So this is, cross section here. So basically at whatever the pressure is at that point during systole, the cuff will immediately increase via the servo control system to prevent the diameter change, therefore keeping the diameter the same. And this is obviously the opposite during diastole. So as soon as systole passes and diastole begins, the cuff immediately drops in pressure. That way it prevents the, the arteries themselves collapsing. It just wants to keep that diameter the same. So the important thing to remember here is that we want the finger cuff pressure to equal the intra-arterial pressure. A bit more about the Physiocal algorithm here. Software does have specific points, which we'll mention, called autocals, that you'll experience when you are using the unit. This happens once every 10 beats at the beginning, but over time, this changes to once every 70 beats until a correct unloaded state has been found within the artery. So what happens here is that we initially start up, you can see in the y-axis here, we have the cuff pressure. This is the plethysmogram here. So, and this is the new set points. So the set point means the unloaded state of the artery. So you can see here that we initially, when you connect this, the pressure is going to keep stepping up until it passes systole. Once it gets to past systole, it's going to drop down, keep at a constant pressure momentarily. So it will measure the actual plethysmogram here. You can actually see, so you actually see how much light is being absorbed by the photodiode. And during this period of calibration, the servo control system within the NIBP will check the amplitude and the shape of the plethysmogram. So based off that, they will then create a set point, which is what they will estimate, what the software estimates to be the unloaded diameter of the artery. And once that's done, then you can actually see during the actual pulses here, the actual finger pressure, that the plethysmogram is almost flat. And the reason why it's flat is because the diameter of the artery is consistent. Therefore, the amount of light passing through stays the same, and that way, we keep it the same. But over time, this has to have an Autocal to correct for any sort of minor adjustments. That's why the first couple of minutes is not as reliable as, let's just say, 5 to 10 minutes later when we have a proper set point, i.e. proper unloaded diameter. So you can see down here, the set point is that it starts here at a certain point. It then has the same set point. And then during this point here, it adjusts it. So if I could actually zoom in here, probably can't do that. That's okay. We actually, with a new set point, it just minutely just adjusts the set point to have a better estimation of what the unloaded diameter is. Therefore, basically, that just means it over time it improves the accuracy of the measurement. Some examples of good Autocal you can see here. So over time, as I mentioned, that following 10 heartbeats, the servo loop system is opened and a stable pressure is applied that is halfway between systolic and diastolic. And at this point, the servo control center within the NIBP examines the shape and the amplitude of the wave, and then it will adjust for what the unloaded volume is optimally at, and then it continues with the blood pressure reading at a more accurate estimation. So when it first starts off, it starts off with 10 beats, Autocal, 10 beats, Autocal, 10 beats, Autocal, then 20, et cetera, et cetera. Normally this takes about 4 minutes. So I'd say about 5 minutes in, you're gonna get the best readings. So with this system itself, as we're all depending on, the fingers to be, nice, the arteries to be nice and plump and easy for light detection to see, quite a few things could go wrong that we need to be aware of. One thing is if it's the wrong cuff size. If the size is clearly too large for a subject's fingers, then the values will be greatly diminished and undervalued. So that's why it's important to look into the cuff size guide, but also if you do notice that the signal looks quite noisy, then I would recommend to drop the cuff size, and you want to see a signal that's fairly clean like this. It's nice and uniform. Improper placement is also a big factor. As I mentioned before, we want to make sure that the light's going below the bone. So that just takes practice to get that in the right position there. Manual will be supplied with you when you looking into this, of course. Cold fingers, in my opinion, is probably the biggest culprit here. So my room here, I'm actually quite cold. So I'm trying to keep my hand warm as best I can before the demo. But naturally, if you have constriction within your arteries, within your fingertips, then this is obviously going to have an effect on how much light is actually being detected. Because if the system itself can't detect heartbeat, then what we're going to see instead is we're actually going to see this inverted image here. So this here shows an example of if someone has cold fingers, then this sequence will arise until it reaches beyond systolic, and then it'll begin to actually show the readings. But even then, the readings may not be entirely accurate. So that's why if you do have cold fingers, I highly recommend warming them up, in some hot water before starting. So that really depends on the subject, but also the conditions of the room. Here you can actually see there are multiple steps. So if you do see multiple steps, that means that the servo control center is just trying to find that proper set point within the arteries to keep them at a unloaded state. So how does it compare to, let's just say the brachial pressure? So generally the finger pressure will be lower than the mean intra-arterial brachial pressure due to a pressure gradient over the arms caused by flow. So this has been, well published in various publications here. Typically we see around 10 millimeters of mercury less in the finger pressure relative to brachial pressure. This study here by Harms et al. 1999 looks into how, we do have a little bit of a time lag between the brachial versus the finger. But for this gentleman that he was in his 20s, the actual waveform itself almost looks identical. Finally, with the system itself, as we are, constantly, increasing and decreasing the finger, the cuff, and keeping the unloaded diameter in the arteries, other blood vessels around these arteries will be collapsed. So what this does mean that is the blood entering the fingertips during systole can only leave during diastole phase. During BP measurements, the fingertip is less obviously sufficiently refreshed, therefore metabolites increase, and also we see an increase in deoxygenation. Hence, you may see some blue fingertips, which obviously will lead to some discomfort over, can take upwards of like, half an hour, 1 hour. So generally when it gets up to 1 hour, we would recommend switching from one cuff to the second cuff. That's the whole point of that. That way we can go for long-term studies. So that's basically all of the slides there. So now it's actually time for me to show you physically the system itself, and we'll actually go through a live demo as well. So the first thing to show is the NIBP wrist unit. So this unit itself is actually quite compact. We can actually see the the front ports there, so the middle being the HCU, one side there being the C1 and the other being C2. And we have our strap here as well, you can actually see. So this is very easy to take off and put it back on. As I mentioned, this has one cable. This one cable here then will connect directly to our NIBP unit. And then here we just have a mains connection and then one USB connection to the computer. The next thing to show would be the HCU, it's a height correction unit. You can see here that this unit itself is about 1 meter or so long. And we have our reference end, that's where the bladder is. And we have our transducer end. So basically this will connect to the finger cuff, while this will be, I'll put this under my shirt and it'll be about the same level as my heart. So as I move my arms up and down, we should see the HCU pressure fairly stable relative to what the raw finger pressure will be. So we'll connect this, obviously, the limo connection will be to the middle. So it will be connected like that. The finger cuff here, you can actually see this is the base. So I suit mostly the medium one. So when we actually, you can see here, we have an air hose and also we have the limo connection. When we unravel this, like so, you notice that I only unravel it that far. I don't actually want to unravel it totally, as I could damage the cuff itself. So it's really important to only go that far. You can notice that we have an LED and a photodiode right there. And inside there, we actually have the air bladder. So how we would connect this, we would actually go, for example, index finger and have it set up just like that. So we don't want it set up, where it's like, looking like this or anything like that. We just want to set it all like, we don't want it down here. We want to set it up this way. Also, we want the cables to run down below the hand like this. We don't want them to go the other way like so, as this could affect the readings. And obviously we don't want to go that way either. So make sure that it's set up just like that. How tight to put these on, you may ask. So I put it on fairly loosely and I just put it on just like that. So it's very easy to put on, very simple setup there. You don't have to like strap it on really hard If it's very tight, that will then overestimate the your reading. So if that happens, then probably bump it up to a higher pressure level. A higher cuff level. So here we're just going to connect the air hose and also going to connect the HCU. So you can see here, that's just for one of these, one cuff. Obviously, if we have a second cuff, then that'll be different. This is the, as you can see here, that this is the guide. So basically you can see we have small, medium, and large. So what you want to do is basically this little strap here, we will put our finger on one end, and I'm just going to wrap it around my finger and do it kind of like that so you can see. So you can see based on this, it's kind of like in between medium, large, but as I said, if it's in between, then go the small version. So that's why I'm going the medium there. Once that's done, this is turned on. We've got this connected to the computer. We can just pretty much open up LabChart now. So share my screen. So the first step is to open up LabChart. When you open up LabChart, you should see there, it says human NIBP is being detected. Right now my Power Lab's turned off. I have a playback file here. That's just a backup extension in LabChart. In the event that this is not working perfectly, then I have something else to show you. Coming up here, when you're actually finding the enabler itself, remember we're using NIBP enabler, that is found on our website. So, if you go to, 80 instruments, go to downloads, and under extensions, there should be the enabler. Once it's found and downloaded, make sure you click on Feature Manager and then scroll down. If you click on All and scroll down, you should see the Human NIBP controller. So you can see there, it says it's compatible with version 8.1.10 or later. And this is the latest version, version 2.0.7. So make sure that's ticked on. The next thing to tick would be the non-invasive cardiac output as well. So make sure that's ticked. Once that's done, you could click on New and start recording, but those aren't actually going to have the parameters for HCU selected. So what we need to do is make sure under Getting Started, we click on Human NIBP, and then we go to Human NIBP INL 382. So that's the product code for this particular, for this Nano. Here's actually the settings file if you have the older version, the ML282. So what we do here is we're going to open this up. And what you can see is that now we have quite a few channels here. We have a few doubling up channels. The reason why is because the HCU is there as a correction factor for any time I move my hands. So you can see here that, okay, I would recommend this settings file if you're moving your arms around. If the subject's staying stationary and not moving, then what you could do instead is just go to Home and click on New, and it'll show you not as many of the files. So for example, if I just want to show you here, if I click on New instead of the settings file, now you can see there's less files here. You can actually see there's HCU pressure, but I don't have the HCU correction for the rest of the files. But that's something I think is important to have. Yes, it's more channels, but that way you can actually see, have a better representation of what the finger pressure is based off the HCU. So the first step here is to connect the transducer and the reference end, go to Setup, then go to Human NIBP HCU and Test. From here, we want to height correction and zero it. This is a test mode we can use just to test the cuff itself. But I mean, to be honest, if it can actually start working, then there's no need to do any testing. So shouldn't worry about this. As you can see here, this is correctly zeroed. Once that's done, let's put it on. So I'm going to put on the strap first. Just a thought here as well for you is that if you're just sitting on the table and not moving your arms, then you don't necessarily need this strapped on. You can just have it next to your hand as well. If that's the strap is too cumbersome for you. You can see here, it's actually fairly easy to connect. So you can see there, pretty straightforward. The next step obviously is my finger cuff. So just going to wrap that around first. So as I mentioned, have the cables below my hand, like so. So remember to have that level. Put it around. Next step is have the transducer connected like so. And then of course we're going to have the HCU, the reference end connected around the level of my heart, as you can see like that. So now we're all set up and ready to go. So all we need to do now is just click on start. It's going to give you a warning window saying, are you ready to sample? And then press start. Once it's ready, we're just going to look at this top channel here. You can see now that the pressure, and I can have that, the feeling is that the cuff is increasing obviously in pressure until it reaches above systolic. Once that happens, you can clearly see that we're getting the readings right there. So we're getting 94, 98, you actually see the readings there. If I zoom in a little, like this, you can actually see the readings there. So I can probably zoom out a bit. So that's clearly showing you there the my diacritic notches. It does a couple of levels of calibration points, and now it just continues. So that's a nice and clean signal. So if I just equalize channel heights again. So the second channel here, you can see that's actually the Hcu correction. So let's actually do a bit of a demonstration here. So we've got the mean arterial pressure here, and we've got the HC mean arterial pressure here. So, and this channel here is a HCU pressure. So if I just, okay. So if you look at now, if we just show you that. So now if I move my hand above my head, notice now the pressure here drops to 54. And notice how the HCU pressure now goes up. That's to do with the hydrostatic pressure. You can see right there. But the HC pressure stays at my original position because of the HCU. And as we drop it back down, then naturally this goes back to, this pretty much stays where it was, whereas this obviously goes back to a similar level. You can see there. So having them pretty much at the same level, so that's at the same level as my heart right now. Therefore, we're getting a pretty good reading. So that just shows you there, that shows you the proof that right now that is the correct reading. Whereas when I drop my fingers lower than my heart level, then the pressure is a little higher than the actual heart level. So that's why the HCU is the one we want to be looking at primarily. As you can see that after a few minutes of demonstrating this, now there's fewer actual set points. There's fewer autocal points. So if I zoom out a little, notice how we had autocals every 10 beats. Now it's much longer because the set point has been found. We found the correct unloaded diameter. So now it doesn't require all those constant autocals. Other channels here you can see. The bottom one here, if I zoom out a little, these are the steps. So this is the autocal step. So when it reaches the bottom of the steps, that's when it autocals. And then of course it goes back up. So notice that when I zoom out a little, the autocals were short. So remember the top, that means how many steps. So it took 10 beats to get to autocal, 10 beats to get to autocal. But as the set point has been found, the correct unloaded diameter, so now the cuff pressure equals the pressure within the artery, it does not need to have constant autocal refreshes. That's why it's longer. And once again, if I move my hand above, you can see that the finger pressure crashes, but the HCU pressure, it stays the same. So pretty handy to use. So if we just equalize channel heights here, you can see we have mean arterial pressure, we have HC systolic, or the systolic, HCU There's diastolic and there's HC diastolic. So just keep looking at the, in my opinion, just looking at the HC, whatever the HC is, those are the values you want to be looking at. This is showing me, obviously, cuff number 1 is being used, how long the cuff is going to be used for. And this is Autocal quality. So Autocal quality tells you the quality of that cuff reading at the moment. You want something like an 8 or a 9. A 9 means it's a really good reading. So you can tell that basically from the actual signal. If the signal looks nice and clean like this, that means the actual, this is working as best as it possibly can right now. So this is a really good demonstration. So now we're actually showing you some other studies, some of how this works. So let's just add some of the cardiac output features as well to it. So if we stop reading at the moment, one thing I can show you here, under human NIBP settings, we have the option of auto calibration enabled. So after a while, like I've done here, if I don't want to show the auto cals anymore, I could disable them like that. If I have errors pop up, by default, LabChart will stop running. But if I want to continue running, I can just click on this and it'll continue to run. Here, the finger pressure is in switching mode. So here I have a switching interval of every half an hour. So even though I've only got one cuff connected here, what I should have done was click on cuff 1. But if I have a second cuff, that way I can switch from one cuff to another. So as I don't have Autocal enabled, what you'll notice is when I press start again, that what we should see is that we're not going to get any more Autocals at all. So it's going to be a constant blood pressure reading. So you can see here now that the blood pressure reading, because it's been about 5 minutes, well, you can see there about 5 minutes, that we're getting a pretty good representation of what the cuffs are. So if you're doing like, beat to beat, heart rate variability, but you don't want any sort of, disruptions, then I'd recommend to record for 5 to 10 minutes, get the proper set point. And once that's done, then you can actually disable the Autocal and actually run it continuously. Because now you're actually going to get a good representation of your blood pressure without having to worry about the Autocals that are getting in the way of your analysis. So you can see there, that's looking nice and clean. Let's now show you the NICO, as I was meant to do. So what to do to actually have extra channels. We go to setup, channel settings, and we're going to add a few more. We're going to add here, we're going to click OK. And what we're going to do is click on non-invasive cardiac output. So here we go. So this works on detecting the end diastolic pressure points. Here we are. So these are finding them clearly based off these parameters here. The minimum peak is 1.5 SD, and we don't have a minimum period here. So this is detecting it fairly easily. What finger pressure it's using, it's using channel 1, and what method is a Wien-Kessel model here. So you can choose between these two. Wien-Kessel requires age, so my age is 35, and you can apply this here. So you can choose between cardiac output, stroke volume, estimated flow, or total peripheral resistance. If you use a less strand, then that one does not require age or gender, but it only shows you 2 output points. So if I just do the Wien-Kessel at the moment, 35, male, click OK, and I can bring out that value here. Notice that it updates immediately what you've done. So I can do the same thing with this one here. So non-invasive cardiac output, less strand. Okay, take it out like that. Press start again. So now you're going to see that as we get to the measuring the finger pressure again, that we'll also get calculations of not only the mean arterial pressure, but also our cardiac output. But we can easily change this to stroke volume. So you can see there, right there will be the actual value. So they're going to pop up. Yep, there we go. 2.4 liters per minute is for left strand, and 3.6 liters per minute is for the Wien-Kessel study. These are showing live data. If you wanted to show more of an averaging, moving average, you can actually click on the settings here and go to average, let's just say every 2 seconds. That way it shows you a bit of a average. It doesn't change every, so often. So you can actually see there that the Wendt cells have a bit of a higher value estimation than the strand right here. So that's basically how the non-invasive blood pressure unit works. Fairly simple. So let's actually go through a few different examples here. So what I also want to show you is, let's say you actually want to connect this to your ECG. So what I might do is put this back on first. So let's say I want to connect my Power Lab. So if I turn my Power Lab on, what I could do is I can go to Setup. I can go to Devices and Channels. If I go to Add New Devices, it will look for my Power Lab, which it's indeed going to find. There it is. And what we're going to do is click on that. And now what we're going to do is add another channel. And this channel is actually going to be, because I've actually got my bioamp connected here as well. They're actually connected. I've got 3 leads connected to my chest. And I'm going to have input 1 because that's where the bioamp's connected. Press OK. So now we have another channel here. And if I just click on this, bioamp, it's detected. I put my mains filter on, change this to like 5 millivolts. Then press start, sampling. So now I'm measuring my ECG from the Power Lab simultaneously, with my finger pressure. So that way, it's a really effective tool if you want to measure both, blood pressure and your ECG simultaneously. So a very cool tool to use here. And if you're interested, with LabChart, you can do all sorts of things here. So for example, if I stop reading, I could like highlight a region like this versus my ECG. And if I go to my zoom view, I can actually see the differences. You can actually see that's my blood pressure and that's my ECG. So there's a bit of a gap there, isn't there? So you can actually look, use the marker from here to there. If you look at the delta, that shows you that the blood pressure reading versus the ECG, we're getting a 0.25 second difference between them. So that's pretty interesting to see. So if you're interested in that sort of thing, then you can do that with LabChart. Finally, what we can show you here is some analysis tools. So, we can do things like heart rate variability. So if I were to select like a region like this, I could then go to HRV, settings, base it off a selection, go on custom and advanced, and make sure I'm actually detecting all my beats. So it looks like I'm detecting them nicely. And going to click OK. They're all purple at the moment because with the HRV module, you need to detect what is ectopic or what is not ectopic. So we're just going to go to classify view and adjust the view here because we're basing ectopic beats off the complexity and the R interval. So complexity is due to the shape, and R intervals obviously, that's given. So that's going to be the difference between one beat to another. So if we just spread this out a bit. By default, it's used for ECG, but we can naturally just adjust some settings here and use it for blood pressure as well. So you can see there that we have our ECG readings. So what you do here is for HRV, you can do things like analysis plots. So, what's our tachogram? So this is actually showing my tachogram. So that's my beats over time. So those are the seconds and those are my beats. And these are the R intervals. So the interval from one beat to another. You can also have things like, your histogram plots, things like that. This will typically be more of a bell-shaped curve when you take more of the sample data, of course. And, you can do things like, power spectrum plots. If you're interested in very small, very, high frequency, low frequency, or very low frequency. But of course, the sample data is too short to have the accurate representation of this spectrum plot. So that's how HRV works. Otherwise, you can use things like the blood pressure. So blood pressure here, if I go, it detects these, it's doing that successfully. And if I do a selection, press OK. So what that does for my blood pressure is I can do things like analysis view. It's actually going to analyze every single beat. So it's going to tell me my end diastolic pressure, my max PDT, my min PDT, and my max pressure points, all within this, all within these each beat. So what that does then allows me to have table view to show you all this data based off your selection. So you can actually see everything to do with my min's pressure, max's pressure, systolic point, diastolic point, and this is every single beat based off these selections here. So that's what that system does there. So we have plenty of tools here, but otherwise, you know, the classic way of collecting data, of course, is, you know, if you want, you can just always select a region. You know, in DataPad, we actually have all the points set up here in the settings file. So this is every single chart channel represented in a separate column. And if we go to multiply to DataPad and use 1 second every second, base that off a selection, and click add, what you'll see now, it's collecting all my data. So if I actually go to my layout view, oh, sorry about that, probably a bit crazy there. Let me just bring that up. Table view. What I wanted to show you was, probably have to just close some of these. Let me just reorganize this. Like so. So basically what I've done with multiply the data pad was I'm now selecting once every second, and you actually see I'm moving across here. So that way I'm not losing any data. I've got everything collected. So it's a really handy tool to use multiply the data pad, or whether you're using blood pressure or HIV anyway. So that's pretty much it. So thank you very much for joining me. This is obviously a recording here. So we'll be sending this to all the people that have registered for the webinar. And if you have any queries, I will also have, you know, the contacts attached to this video at the end of it as well. So thank you so much for watching up, and I hope you enjoyed it and learned something today. So we'll see you around. Take care.